Alrighty, if you're on Zoom, please type something into chat so I can take the roll for those of you that are here. Sheet. Alrighty, today we're going to try to finish up chapter 4 so that we can get into the BJT amplifier chapter as soon as possible. So, let's just real quick. All right, yeah. So the first thing that we're going to talk about today is what's called the early effect. All right. So we said that for an NPN transistor, NPN BJT in the forward active mode, it should look something like this. So let's see. So over here, we will have our, find my notes, there we go, emitter. So this would be our emitter current. Here's our voltage, VBE, which makes the base emitter junction right here forward biased. So there is a very, very small layer of charge, negative charge on the P side of the junction, and an even thinner layer of positive charge stored on the right side of the junction, because this guy is forward biased. Just so we're clear, we have N++ doping here, P+ doping here. And then on this side is our collector. So here's our collector current, IC. Here's our base current, IB. And here's our collector emitter voltage, VCE, which is greater than, let's call it VCE1, which is greater than VBE. And in this case, we have a larger region of negative charge stored on the P side of the base collector junction, and then a relatively large region of positive charge stored on the N side of the base collector junction. And as a reminder, this side is doped N. So we found that in this case, the collector current IC was IS EXP VBE over VT. where IS was the area of the emitter multiplied by Q, charge of an electron, multiplied by the diffusion coefficient of electrons, multiplied by the intrinsic carrier concentration squared, divided by the dopant concentration in the emitter times the width of the base multiplied by exponential VBE over VT minus 1. So IS is equal to this guy right here. So we can observe that the collector current is not a function of the collector emitter voltage. All right. But if we increase VCE, what is physically happening inside our system? Here's IB. E, C, and so let's keep VBE exactly the same, but increase this VCE2 is greater than VCE1. So we are applying a larger reverse bias voltage to the base collector junction. So charge stored over here stays the same at the base emitter junction because VBE has not changed, but the charge stored in the base collector junction does change, right? So if we forward bias it further, that's going to make the depletion region expand, correct? Well, what's happened here is that our width of our base has gotten smaller. And if the width of our base gets smaller, what should happen to IS? Well, let's WB2. So if the width of the base gets smaller, what happens to IS? Width of the base is in the denominator, so as that number gets smaller, IS gets larger, which causes IC to get larger. So we should observe that there is some dependency on the collector current due to a change in the collector emitter voltage. And this phenomenon is what's called the early effect, okay? So what's happening really is that as the width of the base region gets smaller, there is less opportunity for recombination to occur. And if less recombination occurs, then the amount of electrons that move from the emitter to the base to the collector increases. So we see an increase in current. So with the early effect included, our new equation will be IC times IS EXP VBE over VT multiplied by 1 plus VCE over VA, where VA is the early voltage, named after the scientist who discovered it. So it doesn't have anything to do with time. The guy's last name was Early. So now we need to figure out, excuse me, how to determine what the early voltage is, okay? So I'm gonna plot a new characteristic IV curve with the early condition included for a generic BJT transistor. So if we plot IC versus VCE, we know that when VCE is greater than or equal to VBE, we are in saturation. So it's going to look something like this for a given VBE with no early effect. And it's going to look something like this. So it's going to have a slope to it for that same BVE with early effect. Okay. Early voltage is defined as the y-intercept of that sloped line. Right. So the early voltage is if we linearly interpolate that curve in the forward active region back to where it crosses the y-axis, that is our early voltage. Everybody catching what I'm throwing thus far? All right. So the presence of the early effect will slightly change our large signal model. For our NPN transistor. So if here is our base, oops, this is supposed to be a diode. This is still VBE, our current here. IB is still 1 over beta times IC. Our current here, IE, is still the base current plus the collector current. But now we have IC is equal to IS EXP VBE over VT times 1 plus VCE over VA. So it's the exact same large signal model, except that the early effect parameter 1 plus VCE over VA is included. For our small signal model, it's going to cause a reasonably significant change. And so let's talk about that real quick. So our small signal model, just to be clear, we started with this, right? Here's R pi, so we're going to have to take a look at that guy. Here is our base. Here is our emitter. Then we have GM times V pi, where V pi is the base emitter, small signal base emitter voltage. GM is the transconductance. And I think that's it. So that's our starting point for our small signal model, right, with no early effect. So if we look at our transconductance, GM is defined to be the change in the collector current due to a change in the base emitter voltage. So we substitute in our new expression for IC, we get IS EXP VBE over VT 1 plus VCE over our early voltage VA. When we do the indicated derivative, the only thing that comes out is we're going to have IS over VT EXP VBE over VT times 1 plus VCE over VA looks like IC over VT, which is our original definition for our transconductance. So transconductance does not change. If we look at our resistance R pi, that was defined to be beta over the transconductance, which is then just going to be beta VT over IC. So this guy also does not change. But we need to account for the fact that the collector current changes with VCE. So we're going to have some change in IC that is going to be IS VBE over VT 1 plus VCE plus delta VCE divided by VA. So we're changing from one collector emitter voltage to a larger collector emitter voltage. From this, we can see that the change in IC portion is simply IS EXP VBE over VT multiplied by delta VCE over VA. And so now we have a relationship strictly between the change in the collector current due to a change in collector emitter voltage. And we're going to call that R naught. Change in VCE with respect to change in IC is our early voltage VA divided by IS EXP VBE over VT, which is approximately equal to VA over IC. So what that does to our small signal model is it puts a resistance R naught between the collector and the emitter that represents the linear relationship between changes in the collector emitter voltage causing changes in the collector current. I'm sorry, my vet is calling. I need to take this. Hello? I'm doing well. How are you? I think so. Recently, I don't know that it's been too terribly bad, but we've noticed spots on her for a while, and we thought since she was coming in for this, we'd get her looked at. We thought it might have been a food allergy since she's been eating the same food for a couple of months or something like that, but it's a science diet, turkey and something or another, and or no, it's the chicken and the beef. We kind of alternate between those two. We've only noticed them for maybe 2 to 3 weeks, I guess. Okay. Yeah, let's go ahead and do the injection. No, ma'am, thank you so much. Okay, thank you. All right, bye. All right, sorry about that. Okay, so the early effect winds up placing a resistance here between the collector and the emitter, which again relates the change in the collector emitter voltage to the change in the collector current that's flowing. So with that in mind, let's work an example where we want to, let's see, so we're going to have the following circuit. Yes. Sure. VA over IC. What it boils down to. Am I writing like way too fast for you guys? Because I was on the phone for like 4 minutes and people still needed to catch up.
Oh, that was
Okay. Oh, that was off the, okay, I'm sorry. All right. So let's say that we have the following circuit. So we're going to have a 2.5 volt supply voltage applied over this 1 kilo ohm resistor that is connected to our collector. We have 0.8 volts applied at our base. So I'm just going to call this VBE since our emitter is grounded. So here's our base, collector, emitter. Here is our output terminal. So this is a simple common emitter amplifier. Let's say that IS is equal to 5 times 10 to the negative 17 amps. Beta is equal to 100. Our early voltage is equal to 10 volts. So typically, early voltage is somewhere between 5 and 150 volts, just depending on what that slope is. So 10 volts seems like a fairly reasonable early voltage. And our goal is to determine the small signal voltage gain of our system. So we want to determine the small signal voltage gain, which is defined as the small signal output voltage divided by the small signal input voltage of our system, which means obviously we're going to have to use and define all the parameters in our small signal model. But those parameters from our small signal model are defined by the DC operating point of our system, right? So for instance, the transconductance depends on the large signal value of IC, and the resistance R naught also depends on the large signal value of the collector current as well. So just because we're looking for the small signal voltage doesn't mean we don't have to go through and do the large signal analysis to determine the quiescent or operating point of our system. All right, so with that in mind, this is a circuit that we've looked at before, maybe slightly different values. So figuring out the operating point of this guy should be pretty straightforward. Maybe don't even need to use the actual large signal model. And so what I mean is we can see easily that by definition, our collector current should be IS, which is 5 times 10 to the negative 17 amps, times the exponential of 0.8 volts divided by 26 millivolts, which is our thermal voltage, times 1 plus VCE divided by our early voltage of 10 volts. So the only thing that we don't know in this equation to determine our collector current is the collector emitter voltage, which is here. So, do any of you guys have any idea how we might go about getting another relationship for the collector emitter voltage that would allow us to solve for it? We have two equations relating the collector emitter voltage to the collector current. We should be able to solve for both. Okay, so I believe Mr. Martin's argument is that there is a collector current of IC flowing down here, which is the same current flowing through our resistor. So that means that our collector current IC could be expressed as 2.5 volts minus VCE. VCE is the potential, so 2.5 volts is the voltage drop on the top side of the 1 kilo ohm resistor. VCE is the same thing as V out, so it's the potential at the bottom side of the resistor. We divide that by the resistor value itself of 1 kilo ohm, and we now have two equations that we can set equal to each other and then solve for either VCE and or IC from that. So take out your calculators and go ahead and do that for me. All right, so VCE of 1.208 volts, that is also what I got. And substituting that VCE into our equation for IC, we should get 1.292 milliamps. So we know the operating point of our system. Now we can get into our small signal parameters. So transconductance, again, is defined as simply IC over VT. So that's 1.292 milliamps divided by 26 millivolts would give us 49.707 millisiemens. Our pi is beta over GM. So that is 100 over 49.707 millisiemens, gives us 2.011 kilo ohms. And R naught is VA over IC, 10 volts divided by 1.292 milliamps would give us 7.738 kilo ohms. So if we draw our small signal model of our circuit, here's where our pi goes. This is V pi. Emitter, base. This is GM, V pi. Here's R naught. Here is our collector. So this is going to be our input voltage. And we have, let's see. This was a 1 kilo ohm resistor, and VCE is still our small signal output voltage. So how can we figure out what the voltage gain of this guy is going to be? Any thoughts? So yes, Vn is exactly equal to V pi, all right? V out is the drop over the 1 kilo ohm resistor, and also the drop over the resistance R naught, because those two guys are in parallel in the small signal model, right? Because when we turn off our 2.5 voltage source, it's the same as shorting it out to ground. So we consider that to be an AC ground effectively. So I would argue that V out is negative GM V pi, which is the current, multiplied by R naught in parallel with RC. And from this, our voltage gain, AV, is negative GM R naught in parallel with RC. And if we plug in our numbers, we get negative 44.018 volts per volt. Everybody okay with how I determine the gain there? Makes sense. Cameron. The current flowing in, yeah, so that's where the negative sign comes from. So the current flowing into that parallel resistive network is negative GMV pi multiplied by the parallel resistors, gives us current times resistance is our output voltage. What if the early effect were not present? What would our gain be? Would it be larger or smaller? Let's just quantify it in that way. Exactly right. So the early effect, even though it causes the collector current to increase, it actually winds up causing a decrease in the small signal gain of our system. So that's something that we're going to have to pay attention to when we are designing amplifier circuits. Another thing that we haven't talked about yet, and we'll get into in much more detail, right now, this system is unloaded, meaning I do not have a load resistance or anything like that, or load impedance placed between the collector and ground. So that's obviously going to affect our voltage gain as well, because that's putting yet another resistor in parallel with that system, right? So if there was a load resistor here, RL, then our voltage gain for the system would be negative GM R naught in parallel with RC in parallel with our load resistance RL. And so if we choose a very small value of RL, that's going to define what our gain is, not RC. So something to pay attention to for later, and then we'll talk about other topographies that'll get rid of that dependency so that we can get large voltage gains and make good amplifiers. All right, so that is the early effect. Anybody have any further questions or anything on it? Or can we move along here? All right, so with that out of the way, let us talk about operation in the saturation mode. So saturation mode operation occurs when VE is less than VB, but VB is greater than VC. Another way to put this is when VCE is less than VBE. So under that condition, let's look at what's happening internal to our transistor device. Here is our base emitter junction. Here is our base collector junction. Here's our current IB. Here's our current IC. Here's our current IE. Come on, pen thingy. There we go. VBE is greater than 0. VCE is less than VBE. All right, so when VBE is greater than 0, the base emitter junction is forward biased. So our depletion region for our base emitter junction is reduced from the unbiased junction. Here is N++, here's P+, over here is N. How is the base collector junction? Is it forward biased or reverse biased now? So if VCE is less than VBE, that means that VB is greater than VC, right? Because they both have the emitter as a reference, which means that the base collector junction is also forward biased. So negative charge, positive charge. So both of these junctions are forward biased, okay? So let's start by talking about what the holes are going to do, all right? So if both of these junctions are forward biased and we are looking for what's happening with the holes, we should observe that some holes are going to split off and flow from the base to the emitter. And some holes are going to split off and flow from the base to the collector, right? We should have some electron flow from the collector to the base. And we should have electron flow from the emitter to the base, right? But because the emitter is much more heavily doped than the collector, the amount of electrons flowing from the elector to the base is significantly larger than the amount of electrons flowing from the collector to the base, right? So these electrons that are flowing from the emitter to the base are going to diffuse across the base region because there is a big, what would you call it, concentration gradient. like so. And we'll see that the electrons wound up getting collected in the depletion region. The electrons that are leaving the emitter wound up getting collected in the depletion region of the base collector junction, right? So there's no large electric field to sweep them through to the other side. And we're going to see a similar thing about the electrons that are going from the collector to the base, and then will be collected up by the depletion region of the base emitter junction. But again, still there's no field to sweep them through. So overall, what we see is that there's still a large net flow of electrons from left to right, which is what we consider our collector current to be, but the magnitude of that collector current is going to be significantly smaller, okay? Another side effect of having both of these PN junctions forward biased, beta is our common emitter gain, right? Defined as the ratio of IC to IB. Well, our collector current is going down and our base current is going up because it's having to supply more holes to both junctions. So we see that beta degenerates in saturation region operation. And the closer that VCE gets to be VBE, the more and more current we have. So if we were to plot the characteristic curve IC versus VCE, and let's ignore early effects, which should be easy to do because both junctions are forward biased. So if anything, WB is actually getting larger. We should observe something that looks a bit like this. So for a particular value, so if VBE gives us this constant current, what's going on over here is forward active and over here is saturation. Unfortunately, there isn't a particularly good mathematical model available to really better define this curve. I looked in 3 different textbooks and several different online articles, and nothing really has anything to describe what's going on there mathematically too much. The only thing that's really talked about is the concept of hard saturation and soft saturation, or deep saturation and soft saturation, okay? So in deep saturation, which means that VBC the base collector forward bias voltage we actually find that our transistor large signal model looks like this. So we no longer have a dependent current source between the collector and the emitter. We have a fixed bias voltage of 0.2 volts. Okay. In soft saturation, which we'll consider, I can write here, VBC is less than 200 millivolts. We treat the circuit as if it were in the active mode. So effectively what we're saying is until that forward bias voltage across the base collector junction becomes fully on, we shouldn't expect to see a whole heck of a lot of current opposing our collector current, right? So we have a forward bias junction here, right? So I would argue that these two guys, and this isn't in the textbook, this is just me extrapolating what's going on here. This current, so let's call this I flowing from C to B is going to be, let's call it IS2. The forward bias voltage, which is VBC over the thermal voltage. So for very small values of VBC, that current should be roughly negligible. And that's exactly the argument that saying that when we're in soft saturation, we don't really care about that current is making. It's going to be several orders of magnitude smaller than our forward bias current flowing across the base emitter junction. So let's take a look at a couple of example problems dealing with saturation. Okay. Find where I put these are not there. All right. Let's say we have a fairly simple circuit, 2.5 volts, 2 kilo ohms. IS is equal to 6 times 10 to the minus 16 amps. VA is infinity, which is a shorthand notation for saying the early effect doesn't matter. Whenever VA is infinity, then we have 1 plus something over infinity is just 1. So, and whenever VA is infinity in the small signal model, we have an infinitely large impedance, which is the same thing as an open circuit. So just to be clear, VA equals infinity is shorthand notation for ignore the early effect. And beta is equal to 100. We want to calculate two things. What must VB be at the edge of saturation? And B, what must VB, or what is VB at soft saturation? Where VBC is equal to 200 millivolts. All right. So part A of this is very similar to, I think, a homework problem that you guys had to work this past weekend or whatever that was due on Monday, I think. So how might we go about approaching this? So at the edge of saturation, what does that imply? Let's start there. VBE is equal to VCE, or VB is equal to VC, right? So at the edge of saturation, VBE is exactly equal to VCE. Well, we can see VBE is this voltage drop. VCE is this voltage drop. VCE is simply 2.5 volts minus 2 kiloohms multiplied by our collector current, right? Where this guy right here is our collector current. That's just good old Ohm's law for expressing VCE in terms of everything that's going on the right-hand side of our circuit. This gives us VBE is equal to 2.5 volts minus 2 kiloohms times IS EXP VBE over VT, where IS is given to us, and if we're assuming we're operating at 300K, VT is a known quantity as well. And so we can simply solve this guy for VBE. And in doing so, we get VBE is equal to 728.533 millivolts. If you want to take a minute to do that yourself, by all means go ahead, but we're kind of running low on time, so I'm going to feed you answers here to some extent. So anybody have any questions regarding that analysis? All right, fairly straightforward, so I didn't think there would be too much. In soft saturation, we will have VBE is equal to VCE plus VBC. And so this may not be intuitively obvious. But if we were to draw our large signal model here, so here is VBE. Here's our emitter terminal. Here is IS EXP VBE over VT. That's our collector current. IC, here's our emitter current, IE. Here's our base current, IB is equal to 1 over beta IC. Let's see, we have, here is our collector. Actually, let me draw it out here so we can see a bit better. Here is our collector terminal. And then we have a 2 kilo ohm resistor. Here we have our voltage VBE we are trying to determine. But remember also that we have this voltage VBC here, which is 200 millivolts. So if we do Kirchhoff's voltage law, it should be easy to see now why I'm saying that VBE is equal to VBC plus VCE. So I just wanted to be clear about where I got that relationship from. Everybody okay with that? With how I drew the large signal model, and then how I can use the large signal model to verify that this is the correct relationship by just writing a Kirchhoff's voltage law loop around this. All right, so with that in mind, we have VBE is equal to VCE, which is just 2.5 volts minus 2 kiloohms times 6 times 10 to the minus 16 amps exp of VBE over VT. All this guy right here obviously is simply IC plus 200 millivolts. So we have the exact same equation that we had previously, except that there's a plus 200 millivolts tacked onto the end. So when we, sorry, it's going crazy here. Solving this guy, we get VBE is equal to 731.278 millivolts. So we had to change VBE by less than 3 millivolts to get a drop in VCE of 200 millivolts. That's a pretty significant relationship. So it's pretty easy to accidentally drive things deep into saturation if you aren't paying attention, which is what we're going to talk about a whole heck of a lot at the beginning of probably next week or later on Friday with regards to bias circuits. We want these guys to be working in the forward active region if at all possible, because that's where we get amplification. When we're in saturation, that is, if you were to look at it, the transistor as a switch, that's when the switch short circuits, and cutoff mode is when the switch open circuits. So for any type of amplifier circuit, we need to make sure that we're operating in the forward active region where we can get some small signal gain. All right, so any question with regards to that problem or any of the analysis that we did there? Didn't use the large signal model on the first bit there because it was fairly straightforward. Used it to specify the relationship VBE is equal to VCE plus VBC, which allowed us to actually calculate through there. All right, the next problem that I'm working, I found in the textbook, and then it turns out it's actually one of your homework problems that I felt was actually kind of tricky. So I don't have any qualms whatsoever about helping you guys out with this one. Because Dr. Vitari and I argued about it for a good 15 minutes yesterday. So if we can't agree on how to do it, then I feel like you guys are probably going to get super pissed off. All right. So let's say that we have the following circuit. Crap. Here's emitter, collector, Here's our base. Here we have a 100 kilo ohm resistor. We're applying 2.5 volts as a power supply voltage. And our goal is to figure out what resistor value RC will keep VBC, the forward bias voltage of the base collector junction, to less than 200 millivolts. So what's the largest value of RC that will keep this guy in soft saturation? So let's say that IS is 2 times 10 to the negative 17 amps. VA is equal to infinity. Beta is equal to 100. And again, what we want to know is what is the maximum value of RC such that VBC will be smaller than 200 millivolts. Goodness, we got 4 minutes left. All right. So I'm going to draw our large signal model here, and I think this will help us if we don't, even if we don't manage to get all the way through it before class is supposed to be over. Here's our voltage, VBE. Here is our current, IS, EXP, VBE over VT. Down here at the bottom is our emitter, which is tied to ground. Here is our collector. So that's our large signal model for the transistor itself, just for the sake of argument. IB is 1 over beta IC. How are we going to get these resistors? Where should they go? So, between B and C. I disagree. There is a 100 kilo ohm resistor between B and the power supply, and there is a resistor between C and the power supply. So I would argue these guys are tied together. Here is our 2.5 volt supply. I would say that what you just said, putting that resistor between B and C, is a common mistake because it is one that I made the first time I tried to work this out. So I had to go back through it. I was getting wildly weird numbers. And so that's what made me realize that I had made a mistake somewhere. I'm sorry, what? We were just, Dr. Batari and I were just talking about it. We didn't really have anything written down. We were just arguing about the way to approach it. And then when I tried to solve it the first time numerically, I put the resistor between B and C, and that made things wonky. And the reason being is that it's not between B and C. It's between B and the power supply. All right, so we don't know what VB is, right? This is what we would call an example of a self-biased circuit because we're not explicitly applying a fixed voltage to VB. So VB is going to be whatever it needs to be in order to make this guy operate in in soft saturation for a particular value of RC. So in the 1 minute that we have remaining, what relationships can we figure out that might allow us to solve for VBE? Because once we know that, we can figure out pretty much everything else fairly straightforward. I'm sorry, what was that? Okay, so we have our formula for IC, and we know that IB is 1 over beta IC. But how does that help us? We need a little something extra. Okay. I see where I think I see where you're going. So let's do something here real quick, right? So 2.5 volts will be equal to the voltage drop over the 100 kilo ohm resistor, right? Plus the voltage drop VBE. Anybody got any problems with that? So I'm saying it's going to be equal to this voltage, which looks like hot garbage, plus VBE. Well, V100 is what? Let's say in terms of the base current. 100 kilo ohms times IB, right? And plus VBE, but we can express VBE in terms of the base current as well. Or actually, no, let's leave VBE there. We can express the base current in terms of the collector current, which is in terms of VCE, right? And so what I mean by that, 100 kilo ohms, IB is 1 over beta, where we know what beta is, times IS, which we know what that is, EXP, VBE over VT, plus VBE, which allows us to solve for VBE, which I got to be 833.400 millivolts. And that in turn allows me to calculate my collector current, IC, which I get to be 1.667 milliamps. So how would we go from here to determining the resistor value that forces VBC to be 200 millivolts? Because we know that anything larger than that value will make VBC greater than that, right? So I'm going to say that VBC plus here minus here is 200 millivolts. Because that's the situation that I'm trying to figure out what RC value gives me that. And then anything smaller than that should be okay. Anything larger than that will make VBC greater. So putting a base collector voltage of 200 millivolts there, how could I now solve for RC? Right. So yeah, what I would suggest is we do Kirchhoff's voltage law around that loop, right? Where let's call this guy plus VRC. So you would have negative V100 plus VRC minus VBC is equal to 0, which means VBC is equal to VRC minus V100, which is IC, which is known, times RC, which isn't known, minus V100, which is 1 over beta IC, IB, times, let's call it RB. We're trying to find RC, so this means that VBC plus 1 over beta IC RB divided by IC is equal to RC. And there we go. Put numbers in and you're good to go. We're 6 minutes over, so I'll leave that to you guys. But does that approach make sense? We're just using good old Kirchhoff's voltage law, which again has to be valid. It took me a while to figure this one out, and I picked it out of the back of the textbook and was just saying, oh, that's an interesting problem. And Prashana said, yeah, that's one of the homework problems. And I said, oh, I better figure out how to do it. And then it took me a while. So that's why I decided to work it with you guys, so that you would not be so wildly furious about it when you see it. All right, so on Friday, we're going to talk about Pnp transistors, which is going to be pretty quick because it's everything the same as an NPN transistor, except VBE becomes VEB and VCE becomes VEC. It's literally just swap the polarities on those two voltages and everything works out exactly the same. And then we'll get into biasing circuits. All right, see you guys on Friday. Yes. Great question. When is the project due? Lots of people are asking it. I think I said the 20th. So let me look at the calendar here real quick. Yeah. So we have class on the 15th. The 18th is the Martin Luther King holiday. So the 20th would be our first class meeting of next week. That is when I want the project to be completed. So you've still got 1 week's time to get it done.